so I'm going to talk about the need for AI-supported electron microscopy for analyzing asbestos exposure in the working environment. I will be focusing most on the needs and state of play, because the disruption here is, in fact, regulation and what is happening in current situation with aging buildings we have in our countries. So first of all, I'm going to talk a little bit about the background on asbestos, epidemiology, and re-emerging health risks. The EU directive, new requirements regarding asbestos analysis, and then considerations on the new requirements in this directive and the consequences, and then touch upon the solution for the new analytical requirements that are coming out of this directive. So first of all, if you don't know, asbestos is a fibrous material that is basically into mineral groups, amphiboles and serpentines, and was banned in 2005 in Europe, sliding progression since late 70s, early 80s, where the banning was starting, but finally banned in 2005. And it's associated with very serious health effects, and the lag time from exposure to these health effects come up is quite long, can be 1 or 2 decades. So this is still an issue, and here you can see the global distribution of number of deaths in thousands in different types of cancers and asbestosis. And you can also see that from 1990 to 2019, there's pretty much a stable condition, maybe a small increase in the incidence due to basically this lag time from exposure and exposures that could have happened in the meantime after banning. So asbestos is not a fixed problem. It's currently a re-emerging problem because we have a renovation wave that is caught on due to our energy demands. So we try to make better insulation of houses, and the houses are aging, meaning that the building materials that contain asbestos starts to need replacement. So we have roofs, we have interiors that needs replacement. It can be insulations, it can be tiles, it can be paste, etc. A lot of different sources of asbestos exposure. So what is the future risk now, and how can we mitigate the risk? Because together with demolition and renovation is also coming an exposure risk. So the condition can be quite variable. Here we see the development over time of the different deaths reported globally and projected with no change, but there could be incidents where we have increased production and increased exposure related to the renovation wave related to the basically replacement of houses and interiors. So to meet some of these risks and also based on more evidence on the health effects of asbestos, there was a new directive put in place in November 23, where there were some changes that actually has a little bit of disturbance on how we can address asbestos exposure and measure. So until 2029, we can keep in use the same exposure limit as we have today. It's 0.01 fiber per cubic centimeters on a daily exposure, and we measure what is called the WHO fibers, which are fibers that has between 0.2 and 3 micrometers in diameter and a length longer than 5 micrometers. And the methodology to analyze by demand is phase contrast microscopy, so PCM. It's an optical microscope. Or you can use other methods where electron microscopy has been used in the other equivalents. But then, in this directive, there were 2 proposals for occupational exposure limits. So one was to lower the exposure limits to 0.002 fibers per cubic centimeter due to the health risks that is associated with the asbestos fibers. But then there was another option where you could start to measure thinner fibers below 3 microns, and then the exposure limit would be 0.02 fibers per cubic centimeter. But this came with a problem because there was no lower diameter defined in the text for counting, and when you count people, then you need some boundaries for your counting, because otherwise data cannot be comparable and you cannot really put in a regulation that can work in a harmless manner. The asbestos were the same as we knew from before, but there was also new fibers under considerations which are currently not included in regulation. So a number of questions come up now. So what is the accuracy of the asbestos analysis methods and the validity of existing standards developed for the old exposure limit, and can results obtained by the different methods be comparable? Or can we convert data from one method to the other? And here we also have a little bit of a challenge because in the directive it requires a change in the business exposure limit by December 25. But that's 3 years before, 3 years before that they require that we have a transition from phase microscopy to microscopy. So there's a 3-year period where we are a little bit in problem when it comes to established methods. The other question is, can we really have such a high, 5 times higher exposure limit if we count thinner fibers than was in the traditional WHO fiber definition? So is that appropriate? And finally, what are the practical requirements and solutions for how we can determine asbestos with these new limit values? So first, let's take a look at the different methods here. In red, you see areas where the methodology is not compliant with the new requirements. So the phase microscope cannot detect the thin fibers, and it also has problems with the low number concentrations that are in the exposure limits. Whereas the 2 electron microscope or microscopy methods can be used, but they are actually not validated at the concentrations with the new exposure limits. So there are some issues with this, and also some challenges related to these new requirements. There's also sometimes standards that have a deviation. For example, in France, they measure shorter fibers than we do in the WHO definition. So this also results a little bit of difficulty in comparing the results between countries. So phase microscopy is out, the 2 electron microscopes are in, but there are some methodological work to be done. So let's look at the comparability between the methods. So we looked into a comparison between different data sets in the PEROSH working group. And here you see the ratios between the different methods, and this was a little bit disappointing, as you can see, because we have very strong deviations from one, which would be the complete comparability between methods. And also when we did regression analysis between different data sets on same exposure types or exposure samples, we also have a too high scatter between the methodologies. So this actually links to our current practice. We are already in trouble here because we don't really see comparability, and we think that we have a lack of harmonization between labs when they do this kind of analysis. Definitely we cannot convert data from one method to the other without that it's a very stringent set and the lab really knows its own comparability in the analysis. So the other question was, what about these thin fibers that they suddenly propose now as inclusion into the potential new limit value? So we have looked into the existing data again, but here there are some limitations because most studies were not made considering fibers smaller than or thinner than 0.2 micrometers, but we do have some data, and they show that basically we have between 5 to maybe 45% of thinner fibers in the materials that we find. But this cannot really justify that we have a 5 times higher limit value, because we at maximum with the existing data could say, well, at best 2 times the lower limit value. So we don't really see that this could be workable for the same level of protection. But here we also must admit that we need really more studies here to understand what is really the fraction below 200 nanometers or 0.2 microns to really know the numbers below this limit. And also, what should be the lower limit for counting, if that comes to the case. We also have to look into the actual work. Now we move from optical microscopy to electron microscopy. As the workflow can be a little bit different, but basically we need to take a picture, we need to identify a fiber in the picture, whether there are fibers, then we need to measure the fiber thickness and length. And then we need to also understand the chemistry, because there can be lots of different fibers, and you need to know whether the fiber is actually an asbestos fiber, and you determine that with the chemical analysis. And then you compare with your library of chemical composition of the different asbestos types, and then you register the type and morphology and dimensions, and you can go to the next fiber. So you can easily see this is a process that takes a little bit of time. So of course it depends on how much can you put on your filter to analyze. So here we did a calculation based on two scenarios. In red we see the high limit value, where we say that we can identify fibers down to 50 nanometers in diameter. And the other one is the lower limit value, and then we say that we maintain the 200 nanometers as is the WHO fiber. And you can see here that if we consider a traditional sampling time, sampling volume flow of 1.9 liters per minute, we very easily have several hundred of images that we need to take to be able to quantify the concentration at the OL. And normally we would like to be below the OL, so we are certain that the concentrations that we measure are correct. And you also see that we have much more images that we need to take for the higher limit value, because when we need to identify a thin fiber, we need to have high resolution. That means that we can measure on a much smaller area of the filter than with our higher limit value. So this requires actually more work than the lower limit value. So the practical implications is that we need to analyze a lot of frames to analyze the fiber, and we analyze the fibers on the filters, and easily way above 100 frames for one sample, and easily above 300 frames for the higher limit value of the thin fibers. And then we have the safety margin that we would, for example, be 10 times below the limit value, and that means that our analysis becomes very time consuming and costly for practice. So one idea is that, well, we can just put more collect more air to get more filters, get more fibers on our filters, but the problem is that the filters are not living alone in the air. There's a lot of other dust in the air. So basically you end up with this situation, as you see to your left, with a lot of other dust in your sample, and it's impossible to analyze the fiber in such a sample. So we need to be at adequate low volumes, but then cover a larger area of filter to be able to do the analysis. So the solution here is that we propose to switch to AI-supported assisted microscopy, either for the data analysis or image analysis, to do a more cost-efficient approach. And this roadmap requires that we, of course, have input data, so we need a comprehensive set of data with images and chemical spectra to be able to train the system. Here there are further challenges because we need to maybe have this on a laboratory level, but many different microscopes exist with different analytical equipment, and that means that we have a number of different scenarios that we need to analyze. Then we need to decide on the AI approach. So do we do particles alone for fiber identification and then confirmation by energy dispersive spectrometry, so the chemical analysis, or do we do fiber identification and then go back and analyze the sample, or do we do chemical mapping of the entire picture and then put everything into the AI and do instant analysis to determine the fiber dimension and chemistry. This has a very different data requirement and processing requirement behind it. Then we need to train and test. We need to establish the ground truth. That means we need to sit and draw on every image to say this is a fiber and this is not a fiber, to train the AI model, validate, and then performance test. And finally, if we should go all the way to where we are today, we need the standardization phase, and everybody who's done standardization knows that this is not done in a few months. It also takes some time, including inter-laboratory validation and standard development. So this work is in progress. We have a project in Denmark, and we also collaborate with Bauer in Germany, who's also working quite a lot on this, and we are currently in this level where we are training and validating. There are also some market products, but we have tried them out, and they're still challenged with real samples, so there's still some way to go with these as well. So conclusions is that we have methods, but they're not validated for the new asbestos occupational exposure limits. We have a lack of comparability between the different methods, which is a little bit of an issue, also an issue actually when we look into our current data. We also see that the fraction of thin fibers that is proposed to be included in an alternative exposure limit in the new directive, it does really not offer the same protection as the low OEL for WHO fibers, and we recommend that this is further documented in a specific study. And then, due to this extensive process of manual work for doing asbestos analysis, we believe we should just shift to AI-assisted electron microscopy. And here we need a large set of data to be able to do this in a good manner and cover different instrumentation. So thank you very much for your attention, and this is a hi from the PEROSH group on this topic.